Electricity and magnetism are two fundamental forces of nature that were once thought to be completely separate phenomena. For centuries, people observed electric effects, such as sparks from rubbed amber or lightning in the sky, and magnetic effects, such as the mysterious attraction between lodestones and iron, without realizing that these effects were deeply connected. The journey toward understanding their relationship is one of the most important stories in the history of physics, because it reshaped how scientists view forces, energy, and the structure of the universe. In the early study of electricity, scientists focused mainly on static electricity. This involved electric charges at rest, produced by rubbing materials together, storing charge in objects, and observing attraction or repulsion between charged bodies. These effects seemed limited and localized. Static electricity could cause sparks, shocks, and small-scale forces, but it did not appear to have any connection with magnetism. Magnetism, on the other hand, was associated with naturally occurring magnets and their ability to attract iron, align compass needles, and influence navigation. For a long time, magnetism was considered a property unique to certain materials, not something that could be created or controlled in the same way as electricity. The separation between electricity and magnetism began to weaken in the early 19th century. In 1820, Hans Christian Rasted made a groundbreaking observation while lecturing to his students. He noticed that a compass needle deflected when placed near a wire carrying an electric current. This simple observation changed science forever. It showed, for the first time, that electric current could produce a magnetic effect. Electricity and magnetism were no longer isolated topics, they were clearly related. This discovery led to rapid developments by scientists such as Marie Ampère, and Michael Faraday, who explored how electric currents produce magnetic fields and how changing magnetic fields can induce electric currents. Despite these advances, an important conceptual question remained unresolved. What exactly was responsible for creating magnetism? Scientists knew that electric current generated magnetic fields, but an electric current was defined as the flow of electric charge through a conductor. This raised a deeper issue: was magnetism caused by the current as a whole, or was it caused by the motion of individual electric charges? In other words, if electric charges could move without forming a traditional current in a wire, would magnetism still appear? This question touches the very heart of the relationship between electricity and magnetism. If magnetism arises from moving charges, then it is not a separate force at all but a natural consequence of electric charge in motion. This idea suggests a unified view of electromagnetism, where electric and magnetic effects are simply different aspects of the same fundamental interaction. Understanding this unity was crucial for developing a complete and consistent theory of electromagnetism. As scientific understanding progressed, it became clear that motion plays a central role in the connection between electricity and magnetism. A stationary electric charge produces an electric field, but no magnetic field. However, when that same charge begins to move, a magnetic field appears around it. This magnetic field is not an additional substance or force, but a result of how electric fields behave when charges are in motion. This insight helps explain why magnets and electric currents behave the way they do and why magnetic fields always appear alongside moving charges. The realization that electricity and magnetism are interconnected forces also changed how scientists understood matter itself. At the atomic level, electrons move around the nucleus of an atom. These moving charges create tiny magnetic fields, which combine to give materials their magnetic properties. In some materials, such as iron, these microscopic magnetic effects align in a coordinated way, producing strong magnets. In others, the effects cancel out, resulting in little or no magnetism. This microscopic view further reinforced the idea that magnetism is fundamentally linked to the motion of electric charges. The unification of electricity and magnetism reached its most complete form in the work of James Clerk Maxwell in the mid-19th century. Maxwell developed a set of mathematical equations that described how electric and magnetic fields are generated and how they interact with each other. His equations showed that changing electric fields produce magnetic fields, and changing magnetic fields produce electric fields. This mutual relationship led to the prediction of electromagnetic waves, which travel through space at the speed of light. When experiments later confirmed the existence of these waves, it became clear that light itself is an electromagnetic phenomenon. This profound connection has far-reaching consequences. It means that radio waves, microwaves, infrared radiation, visible light, ultraviolet rays, X-rays, and gamma rays are all forms of electromagnetic radiation. They differ only in frequency and wavelength, not in fundamental nature. The technologies that define modern life, including radios, televisions, mobile phones, Wi-Fi, medical imaging, and satellite communication, all rely on the principles of electromagnetism. At the core of all these applications lies the idea that electric and magnetic fields are inseparable and arise from electric charges and their motion. Understanding that electricity and magnetism are deeply connected also changes how we interpret everyday phenomena. When an electric motor operates, electric currents flow through coils, creating magnetic fields that interact with other magnetic fields to produce motion. In a generator, mechanical motion causes charges to move, generating electric currents through magnetic induction. These processes are two sides of the same principle, the interplay between electric charges, motion, and magnetic fields. Without the unity of electricity and magnetism, such devices would be impossible to explain or design. The importance of this connection extends beyond practical technology into fundamental physics. Albert Einstein's theory of special relativity later revealed that electric and magnetic fields are not absolute, but depend on the observer's frame of reference. What appears as a purely electric field in one frame may appear as a combination of electric and magnetic fields in another. This means that magnetism itself can be understood as a relativistic effect of electric forces. Such insights further confirm that electricity and magnetism are not separate forces, but different manifestations of a single electromagnetic interaction. In the broader context of scientific thought, the unification of electricity and magnetism stands as one of humanity's greatest intellectual achievements. It shows how careful observation, experimentation, and reasoning can reveal deep connections between seemingly unrelated phenomena. The recognition that moving electric charges create magnetic effects paved the way for experiments like Rowland'S, which provided direct evidence for this principle. These experiments did not merely confirm existing ideas, they strengthened the conceptual foundation of electromagnetism and helped transform physics into a more unified and coherent science. By understanding the deep connection between electricity and magnetism, scientists gained a powerful framework for exploring nature. This framework continues to guide research in fields such as plasma physics, astrophysics, quantum mechanics, and modern electronics. From the behavior of charged particles in space to the functioning of advanced technologies on Earth, the unity of electricity and magnetism remains a central theme. In essence, the idea that electricity and magnetism are deeply connected represents a shift from viewing nature as a collection of separate forces to seeing it as an interconnected system governed by fundamental principles. This idea not only explains how moving charges create magnetic fields, but also reveals a deeper harmony in the laws of physics. It is this harmony that underlies both the elegance of scientific theory and the practical power of modern technology. The deep connection between electricity and magnetism also transformed the way scientists understood forces in nature and encouraged them to search for unity among physical laws. Before this connection was established, forces were studied in isolation. Gravity explained falling objects and planetary motion. Electricity explained sparks and attraction between charged bodies, and magnetism explained compasses and lodestones. Each force seemed to follow its own rules. The realization that electricity and magnetism were intertwined suggested that nature might be governed by fewer fundamental forces than previously believed. opening the door to unification as a guiding principle in physics. One of the most important consequences of linking electricity and magnetism was the shift from thinking in terms of direct forces between objects to thinking in terms of fields. An electric charge does not simply pull or push another charge at a distance. Instead, it creates an electric field in the space around it. Similarly, a moving charge creates a magnetic field in the surrounding space. These fields exist independently of whether another object is present to detect them. This field-based view allowed scientists to explain how energy and information could travel through empty space, something that was difficult to understand using older force-based ideas. The concept of fields also helped clarify why motion is essential in the creation of magnetic effects. A stationary charge produces a static electric field that does not change with time. However, once the charge begins to move, the electric field changes, and this change gives rise to magnetic effects. In this sense, magnetism can be seen as a dynamic aspect of electricity. It emerges naturally when electric charges are in motion, reinforcing the idea that magnetism is not an independent phenomenon but a companion to electricity. This understanding played a crucial role in explaining natural phenomena beyond the laboratory. For example, Earth itself behaves like a giant magnet, with a magnetic field that protects the planet from harmful solar radiation and guides compass needles. Scientists now understand that this magnetic field is generated by the motion of electrically charged particles in the molten outer core of the Earth. The movement of these charges, driven by heat and rotation, creates electric currents that produce Earth's magnetic field. This is a powerful real-world example of how moving charges give rise to magnetism on a planetary scale. Similarly, the magnetic fields of the Sun and other stars are generated by the motion of charged particles in extremely hot plasma. These magnetic fields influence solar flares, sunspots, and space weather, which can affect communication systems and power grids on Earth. Once again, the underlying principle is the same: motion of electric charges leads to magnetic effects. The unity of electricity and magnetism allows scientists to apply the same basic laws to understand phenomena ranging from microscopic particles to massive celestial bodies. The connection between electricity and magnetism also reshaped how energy is transmitted. Before electromagnetic theory was fully developed, it was unclear how energy from an electric source could travel across space without a physical medium. Maxwell's work showed that oscillating electric and magnetic fields can sustain each other and propagate as electromagnetic waves. These waves do not require a material medium; they can travel through a vacuum. This insight explained how sunlight reaches Earth and how radio signals can travel vast distances through space. As technology advanced, this theoretical understanding became the foundation for countless practical applications. Electric power transmission relies on the controlled motion of charges through conductors, producing magnetic fields that are essential for transformers and motors. Wireless communication depends on accelerating charges in antennas, which generate electromagnetic waves that carry information. Even modern computing relies on electromagnetic principles, from the flow of electrons in circuits to the magnetic storage of data. The deep connection between electricity and magnetism also influenced how scientists think about measurement and experimentation. Experiments such as Rowland'S were designed precisely to isolate the role of moving charge and demonstrate that magnetism does not require a conventional current in a wire. These experiments reinforced the idea that what truly matters is charge motion itself, not the specific material or setup used to produce that motion. This insight encouraged more refined experiments and led to a clearer understanding of the microscopic origins of electromagnetic phenomena. At the atomic and subatomic levels, the unity of electricity and magnetism becomes even more apparent. Electrons possess electric charge and intrinsic motion, including spin, which gives rise to magnetic moments. The magnetic behavior of atoms and molecules depends on how these tiny magnetic moments interact and align. Quantum mechanics later provided a deeper explanation for these effects, but the foundation remained electromagnetic in nature. Without recognizing the connection between electricity and magnetism, such explanations would be incomplete. The influence of this connection extends into modern scientific research. Particle accelerators use electric fields to accelerate charged particles to high speeds and magnetic fields to steer and focus them. Medical technologies such as MRI scanners rely on strong magnetic fields and electromagnetic signals to produce detailed images of the human body. These technologies demonstrate how theoretical insights about electricity and magnetism can lead to life-changing applications. On a philosophical level, the unification of electricity and magnetism changed how scientists approach knowledge itself. It showed that nature often operates through underlying principles that may not be immediately obvious. Phenomena that appear different on the surface may share a common origin when examined more deeply. This realization encourages scientists to look for patterns, symmetries, and connections rather than treating each observation as an isolated fact. The idea that electricity and magnetism are deeply connected also had a profound impact on education and scientific communication. Physics textbooks, lectures, and experiments began to emphasize electromagnetism as a unified subject rather than separate topics. This unified approach makes it easier for students to grasp complex ideas and see how different concepts fit together. It also reflects the true nature of physical reality more accurately. As scientific knowledge continues to evolve, the connection between electricity and magnetism remains a cornerstone of our understanding of the universe. Even newer theories, such as quantum electrodynamics and the Standard Model of particle physics, build upon classical electromagnetic principles. These advanced theories describe how charged particles interact through electromagnetic forces at the most fundamental level. Yet they still reflect the same basic idea: electric charge and its motion are central to magnetic effects. In everyday life, people may not consciously think about the unity of electricity and magnetism, but they experience its consequences constantly. Turning on a light, using a smartphone, listening to music through speakers, or navigating with GPS all depend on electromagnetic principles. The seamless integration of these technologies into daily routines is a testament to how thoroughly the connection between electricity and magnetism has been harnessed. Ultimately, the deep connection between electricity and magnetism represents more than just a scientific discovery. It represents a way of thinking about nature that values unity, coherence, and simplicity beneath apparent complexity. By recognizing that moving electric charges create magnetic effects, scientists uncovered a fundamental truth that links theory with experiment, microscopic behavior with cosmic phenomena, and abstract equations with practical technology. This understanding continues to inspire exploration and innovation, reminding us that the laws governing the universe are both elegant and profoundly interconnected. Electric charge is one of the most basic properties of matter, yet its behavior changes dramatically depending on whether the charge is at rest or in motion. Understanding the difference between static charges and moving charges is essential for grasping how electric and magnetic phenomena arise and why magnetism does not appear in situations involving charges at rest. This distinction played a crucial role in the development of electromagnetic theory and directly influenced experiments such as Rowland'S, which aimed to reveal the true origin of magnetic effects. Static electric charges are charges that are not moving relative to an observer. These charges can exist on the surface of objects, such as when a plastic rod is rubbed with cloth, or when a balloon sticks to a wall after being rubbed on hair. In such cases, electrons are transferred from one material to another, creating an imbalance of charge. The charged object then produces an electric field in the space around it. This electric field exerts forces on other charged objects, causing attraction or repulsion depending on the nature of the charges involved. All observable effects in static electricity can be explained by electric fields alone, without invoking magnetism. One of the defining characteristics of static charges is that they create electric fields that are steady and unchanging with time, as long as the charges remain at rest. These fields radiate outward from positive charges and inward toward negative charges, forming patterns that can be visualized using electric field lines. The strength of the electric field depends on the amount of charge and the distance from it, but not on any magnetic property. No matter how large the static charge is, it does not generate a magnetic field simply by existing. This fact puzzled early scientists who were trying to understand the relationship between electricity and magnetism. Static electricity was one of the first electrical phenomena to be studied systematically. Ancient Greeks noticed that amber, when rubbed, could attract small objects like feathers or bits of straw. For centuries, this behavior was considered mysterious and unrelated to magnetism, which was observed separately in lodestones and compass needles. Even as scientific understanding advanced, static electricity and magnetism remained distinct subjects because static charges showed no magnetic influence. This separation reinforced the belief that electricity and magnetism were fundamentally different forces. In contrast, moving electric charges exhibit entirely different behavior. When charges begin to move, they not only produce electric fields but also generate magnetic fields. This motion can occur in various forms, such as electrons flowing through a wire, charges moving across a surface, or charged particles traveling through space. The presence of motion transforms the situation, introducing magnetic effects that cannot be explained by electric fields alone. This is the key distinction between static and moving charges and the foundation of electromagnetic phenomena. An electric current is one of the most familiar examples of moving charges. In a metal wire, free electrons drift through the lattice of atoms when a voltage is applied. Although the individual electrons move relatively slowly, their collective motion constitutes an electric current. Experiments in the early 19th century showed that such currents produce magnetic fields around the wire. The direction and strength of the magnetic field depend on the direction and magnitude of the current, demonstrating a clear link between charge motion and magnetism. The discovery that electric currents create magnetic fields raised an important question: is magnetism caused by the current as a whole, or by the motion of individual charges? At first, the concept of current dominated thinking, because current was easier to measure and manipulate in experiments. However, current is simply a macroscopic description of many charges moving together. At a deeper level, it is the motion of each charged particle that contributes to the magnetic field. This realization shifted scientific focus from currents to charge motion itself. Moving charges produce magnetic fields because motion changes how electric fields are perceived in space. A stationary charge creates an electric field that is symmetrical and static. When the charge moves, the symmetry of the electric field is altered, and this alteration manifests as a magnetic field. The magnetic field always appears perpendicular to the direction of motion of the charge and the electric field it produces. This geometric relationship is a fundamental feature of electromagnetism and explains why magnetic forces act differently from electric forces. Another important difference between static and moving charges lies in the forces they experience. Static charges exert electric forces on each other that act along the line connecting them. These forces can attract or repel but do not depend on motion. Moving charges, however, experience additional forces when they move through magnetic fields. This magnetic force depends on the velocity of the charge and acts perpendicular to both the direction of motion and the magnetic field. As a result, magnetic forces can change the direction of motion of a charge without changing its speed, something electric forces alone cannot do. This distinction helps explain many natural and technological phenomena. For example, charged particles trapped in Earth's magnetic field spiral along magnetic field lines rather than moving directly toward or away from the planet. This behavior cannot be explained using static electricity alone. it requires an understanding of how moving charges interact with magnetic fields. Similarly, the circular motion of electrons in particle accelerators relies on magnetic forces acting on moving charges, allowing scientists to control particle trajectories with great precision. Static charges also differ from moving charges in how energy is stored and transferred. In static electricity, energy is stored in electric fields. When charges move, energy can be transferred between electric and magnetic fields, allowing electromagnetic energy to propagate through space as waves. This dynamic interplay is absent in purely static situations. Without moving charges or changing fields, electromagnetic waves cannot exist, highlighting once again the special role of motion in electromagnetic phenomena. The contrast between static and moving charges also appears at the microscopic level. Inside atoms, electrons are in constant motion around the nucleus. Even though an atom may be electrically neutral overall, the motion of its electrons creates tiny magnetic effects. In many materials, these effects cancel out due to random orientations. In certain materials, however, the motions and spins of electrons align in a coordinated way, producing macroscopic magnetism. This atomic scale behavior demonstrates that magnetism ultimately arises from moving charges, even when no visible current is present. Understanding the difference between static and moving charges was essential for resolving long-standing puzzles in physics. For example, why does a current-carrying wire attract a compass needle, while a charged object at rest does not? The answer lies in the presence or absence of charge motion. The wire contains moving charges that generate a magnetic field, while the static charged object does not. This simple distinction clarifies many experimental observations that once seemed confusing or contradictory. The distinction also influenced experimental design in electromagnetism. Scientists realized that to study magnetic effects, they needed to create situations where charges were in motion. This led to increasingly sophisticated experiments involving rotating charged objects, flowing currents, and moving charged particles. Rowland's experiment, in particular, was designed to show that even when charges move without forming a conventional current in a wire, magnetic effects still appear. This directly demonstrated that motion itself, not the specific form of current, is the essential factor. Historically, the separation between static and moving charges shaped the progression of scientific ideas. Early theories treated electricity and magnetism as unrelated because static charges showed no magnetic behavior. Only when scientists began to focus on moving charges did the connection become clear. This shift in perspective required abandoning older assumptions and adopting a more unified view of physical forces. The distinction between static and moving charges also has educational importance. Students often first encounter electricity through static phenomena, such as rubbing objects and observing attraction. While these examples are useful, they can give the impression that electricity is limited to simple push and pull interactions. Introducing moving charges reveals a richer and more dynamic picture, where electricity and magnetism interact in complex and fascinating ways. This progression mirrors the historical development of the field and helps learners build a deeper understanding. In everyday life, the difference between static and moving charges is constantly at work. Static electricity may cause minor shocks or make objects cling together, but moving charges power homes, drive machines, and transmit information. The technologies that define modern civilization depend almost entirely on the controlled motion of electric charges and the magnetic effects that accompany them. Without understanding how moving charges differ from static ones, it would be impossible to design or operate these technologies effectively. Ultimately, the contrast between static charges and moving charges reveals a fundamental truth about nature. Motion matters. A charge at rest and the same charge in motion are not equivalent in their physical effects. Motion introduces magnetism, changes how forces act, and allows energy to flow through space in new ways. This insight laid the groundwork for the unification of electricity and magnetism and prepared the way for experiments and theories that transformed physics. By recognizing the crucial role of charge motion, scientists uncovered the deeper structure of electromagnetic interactions, a structure that continues to shape our understanding of the universe. The difference between static and moving charges also becomes clearer when considering how they behave in different reference frames. A charge that appears stationary to one observer may be moving relative to another observer. This raises an important question. Does magnetism depend on absolute motion or on relative motion? Modern physics shows that magnetic effects depend on motion relative to the observer. What one observer describes as a purely electric field from a stationary charge, another observer moving alongside that charge may interpret as a combination of electric and magnetic fields. This insight, later formalized through the theory of relativity, reinforces the idea that static and moving charges are not fundamentally different entities, but different descriptions of the same physical reality. This perspective helps explain why magnetism can be seen as a consequence of electric forces viewed from a moving frame of reference. When charges move, the electric forces between them are modified by relativistic effects such as time dilation and length contraction. These modifications give rise to what we interpret as magnetic forces. From this viewpoint, magnetism does not introduce a new type of interaction, but emerges naturally from electric interactions when motion is involved. This understanding provides a deeper conceptual link between static electricity and magnetism, uniting them at a fundamental level. The practical implications of this distinction are especially important in engineering and technology. In electrical circuits, charges are constantly in motion even if the overall system appears stable. The design of wires, circuit boards, and electronic components must account for both electric and magnetic effects produced by moving charges. For instance, high-speed electronic circuits can generate unwanted magnetic fields that interfere with nearby components. Engineers must carefully manage charge motion to minimize such effects, demonstrating how deeply the behavior of moving charges influences modern technology. In power systems, the distinction between static and moving charges is also critical. Static charges can accumulate on the surfaces of conductors and insulators, sometimes leading to sparks or electrical discharges. While these effects can be dangerous, they are generally localized and short-lived. Moving charges, on the other hand, form steady currents that can deliver large amounts of energy over long distances. The magnetic fields associated with these currents are essential for transformers, which rely on changing magnetic fields to transfer energy between circuits. Without moving charges, large-scale power distribution would not be possible. The role of moving charges is equally important in communication technologies. Radio transmission involves accelerating charges back and forth in an antenna. This acceleration creates changing electric and magnetic fields that propagate through space as electromagnetic waves. A static charge, no matter how large, cannot radiate energy in this way. Only when charges move, and especially when their motion changes with time, can information be transmitted wirelessly. This highlights the fundamental limitation of static charges and the unique capabilities introduced by charge motion. In natural environments, the distinction between static and moving charges explains phenomena such as lightning and auroras. Lightning begins with the buildup of static charges in storm clouds, but the dramatic flash occurs when these charges suddenly move, forming a powerful current through the air. The movement of charges generates intense magnetic fields and electromagnetic radiation, producing light, sound, and heat. Similarly, auroras are caused by charged particles from the sun moving through Earth's magnetic field and colliding with atmospheric gases. Static charges alone cannot account for these dynamic and energetic displays. The difference between static and moving charges also affects how forces act on materials. Static electric forces can attract or repel objects, but they do not typically cause sustained motion in conductive systems. Moving charges, through their interaction with magnetic fields, can produce continuous motion as seen in electric motors. In a motor, electric currents flowing through coils create magnetic fields that interact with external magnetic fields, producing rotational motion. This process depends entirely on the behavior of moving charges and would be impossible with static charges alone. From a scientific perspective, distinguishing between static and moving charges guided the development of experimental methods. Sensitive instruments were designed to detect electric fields produced by static charges and magnetic fields produced by moving charges. As experimental techniques improved, scientists were able to observe subtle magnetic effects from non-traditional sources of charge motion, such as rotating charged objects or beams of charged particles. These observations confirmed that magnetism is a universal consequence of charge motion, regardless of how that motion is produced. At the microscopic scale, the distinction also helps explain why certain materials respond differently to electric and magnetic fields. Insulators can support static electric charges on their surfaces but do not allow charges to move freely. As a result, they can exhibit strong electric effects but weak magnetic effects. Conductors, in contrast, allow charges to move easily, making them central to magnetic phenomena associated with currents. Semiconductors occupy a middle ground, where charge motion can be carefully controlled, enabling the sophisticated electronic devices used today. The evolution of scientific theory further blurred the sharp line between static and moving charges. Maxwell's equations showed that even a changing electric field, without actual charge motion, can produce a magnetic field. This means that motion is not limited to physical movement of charges, but can also involve changes in electric fields over time. Nevertheless, these changing fields are ultimately linked to the behavior of charges somewhere in the system, preserving the fundamental role of charge dynamics in magnetism. In educational contexts, emphasizing the difference between static and moving charges helps students understand why certain experiments produce magnetic effects while others do not. It also clarifies common misconceptions, such as the belief that any electric charge automatically produces magnetism. By carefully distinguishing between rest and motion, learners can build a more accurate and intuitive understanding of electromagnetic phenomena. The distinction also has safety implications. Static electricity can cause minor shocks or ignite flammable vapors, while moving charges in high-current systems can generate strong magnetic forces, heat, and radiation. Understanding these differences allows scientists, engineers, and technicians to design safer systems and respond effectively to hazards. It reinforces the idea that charge behavior must be understood not only in terms of amount, but also in terms of motion. Ultimately, the contrast between static and moving charges deepens our appreciation of the dynamic nature of the physical world. A charge at rest represents a state of stored potential, while a moving charge represents action, interaction, and transformation. Magnetism, electromagnetic waves, and many forms of energy transfer arise only when charges move or when electric fields change. This insight connects everyday experiences with deep physical laws and shows how a simple distinction can unlock a profound understanding of nature. By recognizing how static charges differ from moving charges, scientists were able to move beyond fragmented explanations and toward a unified theory of electromagnetism. This understanding laid the foundation for experiments like Rowland'S and for the technologies that shape modern life. It reminds us that motion is not merely a detail, but a defining feature of how electric and magnetic phenomena emerge and interact throughout the universe. Henry Augustus Rowland was one of the most influential physicists of the 19th century, and his contributions played a crucial role in shaping modern electromagnetic theory. Born in 1848 in the United States, Rowland lived during a period when physics was undergoing rapid transformation. Scientists were moving away from purely descriptive ideas toward experimental precision and mathematical clarity. Electricity and magnetism were among the most actively studied subjects of the time, yet many fundamental questions remained unanswered. Rowland entered this scientific environment with a strong belief in careful experimentation, accuracy, and the need to test theoretical ideas through direct physical evidence. Rowland's early scientific work already reflected his commitment to precision. He was deeply interested in measurement and instrumentation, believing that progress in physics depended on improving the accuracy of experimental methods. This attitude distinguished him from many of his contemporaries. While some physicists focused mainly on developing theories, Rowland emphasized the importance of verifying those theories with reliable experiments. This mindset later became central to his most famous contribution, the experimental demonstration that moving electric charge produces magnetism. During Rowland's time, the idea that electric currents generate magnetic fields was well established. However, a subtle but important question remained unresolved. An electric current was defined as the flow of charge through a conductor, such as a wire. But was magnetism produced by the current as a whole, or was it produced by the motion of electric charges themselves? This distinction was not merely philosophical, it touched the core of electromagnetic theory. If magnetism arose directly from moving charges, then magnetism was not a separate phenomenon, but a direct consequence of electricity in motion. Rowland recognized that this question could not be answered by theory alone. It required an experiment that isolated charge motion from conventional electric current. At the time, many physicists assumed that magnetism was inseparable from current-carrying conductors. Rowland challenged this assumption by designing an experiment that involved moving electric charges without using a traditional wire-based current. This bold approach reflected his willingness to question established ideas and rely on experimental evidence rather than accepted definitions. The experiment that made Rowland famous involved a rotating disc coated with electric charge. Instead of allowing charges to flow through a wire, Rowland arranged for the charges to move simply by rotating the charged object. When the disc was stationary, the charges were at rest and produced only an electric field. When the disc rotated, the charges moved along circular paths. According to the hypothesis Rowland sought to test, this motion alone should be sufficient to generate a magnetic field. Designing such an experiment was extremely challenging, especially given the technological limitations of the late 19th century. The magnetic effects produced by the moving charges were expected to be very small. Detecting them required exceptional sensitivity and careful elimination of possible sources of error. Rowland's skill as an experimentalist was crucial here. He employed highly sensitive magnetic detectors and took great care to ensure that any observed magnetic effect could only be attributed to the motion of charge, not to stray currents or external magnetic influences. When the experiment was conducted, the results were clear and groundbreaking. As the charged disc rotated, a magnetic effect was detected. When the direction of rotation was reversed, the direction of the magnetic effect also reversed. When the disc stopped, the magnetic effect disappeared. These observations provided direct experimental proof that moving electric charges produce magnetic fields. The experiment confirmed that magnetism does not require a conventional electric current in a wire. It arises whenever electric charge is in motion. Rowland's contribution was significant not only because of the result itself, but also because of what it clarified conceptually. His experiment demonstrated that an electric current is simply one particular way of organizing charge motion. At a deeper level, magnetism is linked to motion itself, not to the material structure of conductors. This insight helped unify the concepts of electricity and magnetism and supported the emerging electromagnetic theory developed by James Clerk Maxwell. At the time of Rowland's work, Maxwell's equations had already been published, but their physical interpretation was still being explored and debated. Maxwell's theory predicted that moving charges should produce magnetic fields, but experimental confirmation was essential for widespread acceptance. Rowland's experiment provided precisely this confirmation. It strengthened confidence in Maxwell's framework and helped convince the scientific community that electricity and magnetism were fundamentally connected aspects of a single phenomenon. Rowland's impact extended beyond this single experiment. He was also deeply involved in advancing scientific education and research infrastructure in the United States. As a professor at Johns Hopkins University, he played a key role in establishing one of the first research-oriented physics programs in the country. He believed that students should not merely learn existing knowledge, but actively participate in experimental investigation. This philosophy helped shape the future of American physics and inspired generations of scientists. In addition to his work on electromagnetism, Rowland made important contributions to spectroscopy. He developed high-quality diffraction gratings that greatly improved the resolution of spectral measurements. These gratings allowed scientists to analyze light with unprecedented precision, leading to advances in atomic physics and astronomy. Although this work may seem unrelated to electromagnetism, it reflected the same commitment to experimental accuracy that characterized his approach to Rowland's experiment. Rowland's scientific reputation was built on his insistence that physical theories must be grounded in observable reality. He was skeptical of vague explanations and demanded quantitative agreement between theory and experiment. This attitude sometimes brought him into disagreement with other scientists, but it also earned him great respect. His work demonstrated that careful experimentation could resolve deep theoretical questions that might otherwise remain speculative. The broader significance of Rowland's contribution lies in how it changed the way scientists thought about magnetism. Before his experiment, magnetism was often associated primarily with permanent magnets or current-carrying wires. After Rowland, it became clear that magnetism is a general consequence of charge motion, regardless of how that motion is produced. This understanding paved the way for later developments in atomic physics, where the magnetic properties of materials are explained in terms of moving electrons within atoms. Rowland's work also anticipated ideas that would later emerge in relativistic physics. Although he did not frame his results in terms of relativity, his experiment supported the idea that electric and magnetic phenomena depend on motion. This idea would later be formalized by Albert Einstein, who showed that electric and magnetic fields transform into one another depending on the observer's frame of reference. In this sense, Rowland's experiment contributed indirectly to the conceptual foundation of modern physics. The historical importance of Rowland's contribution is sometimes overlooked, but it remains a cornerstone in the experimental study of electromagnetism. His work demonstrated how a carefully designed experiment could illuminate the fundamental nature of physical forces. It also showed that progress in science often requires questioning assumptions and finding new ways to test ideas that seem abstract or theoretical. Rowland's legacy is not limited to a single discovery. It includes his role as a teacher, his contributions to experimental technique, and his influence on the development of physics as a rigorous, research-driven discipline. By proving that moving electric charges create magnetic fields, he helped bridge the gap between theory and experiment and brought clarity to one of the most important concepts in physics. In the context of electromagnetic history, Henry Augustus Rowland stands as a figure who combined intellectual curiosity with experimental excellence. His work exemplifies how scientific understanding advances through precise measurement, careful reasoning, and the courage to challenge established views. The principles confirmed by his experiment continue to underpin modern science and technology, making his contribution both historically significant and enduring in its impact. The influence of Henry Augustus Rowland's work continued to grow after his experimental results became known, shaping both scientific thinking and future research directions. His experiment did more than confirm an abstract theoretical prediction. It changed how physicists defined and interpreted electric current itself. After Rowland's findings, current was no longer viewed simply as something that existed only inside wires. Instead, it became understood as any organized motion of electric charge, regardless of whether that motion occurred in a solid conductor, on a surface, or in empty space. This broader definition allowed electromagnetic theory to be applied more universally and with greater conceptual clarity. Rowland's contribution also helped bridge a gap between macroscopic and microscopic explanations of magnetism. Before his work, magnetism was often explained in terms of bulk materials and large-scale currents. His experiment made it easier to extend magnetic explanations down to the level of individual charges. If moving charge produces magnetism, then the magnetic properties of matter must ultimately arise from the motion of charged particles inside atoms. This idea later became essential in explaining phenomena such as paramagnetism, diamagnetism, and ferromagnetism, all of which depend on the behavior of electrons. The scientific community's response to Rowland's experiment reflected its importance. Physicists recognized that his work provided one of the clearest experimental demonstrations of the unity of electricity and magnetism. It resolved lingering doubts about whether magnetic effects required special conditions or materials. By showing that simple motion of charge was sufficient, Rowland removed ambiguity and strengthened confidence in electromagnetic theory. His experiment became a reference point in discussions about the physical meaning of magnetic fields. Rowland's insistence on experimental rigor also set a standard for future research. He was known for his meticulous attention to detail and his refusal to accept results that could not be clearly justified. This approach influenced the culture of physics laboratories, particularly in the United States, where he helped establish experimental physics as a discipline grounded in precision rather than approximation. His laboratory methods emphasized careful calibration, error analysis, and repeatability, practices that remain central to scientific research today. Beyond the laboratory, Rowland's work had implications for how physics was taught and communicated. His findings provided educators with a concrete example to illustrate abstract electromagnetic concepts. Instead of relying solely on mathematical equations or indirect reasoning, teachers could point to Rowland's experiment as clear evidence that motion of charge creates magnetism. This helped students develop a more intuitive understanding of electromagnetic phenomena and reinforced the idea that theory and experiment are inseparable. Rowland's role as an educator was as significant as his role as a researcher. At Johns Hopkins University, he helped shape one of the first graduate-level physics programs in the United States. He encouraged students to engage directly with experiments rather than passively absorbing established knowledge. Many of his students went on to become influential scientists themselves, carrying forward his emphasis on precision and critical thinking. Through his teaching, Rowland's influence extended far beyond his own published work. The broader scientific context of Rowland's contribution also highlights its lasting relevance. His experiment came at a time when physics was moving toward greater unification. The success of electromagnetic theory inspired scientists to search for similar unifying principles in other areas, such as thermodynamics and optics. Rowland's work demonstrated that unification was not merely a philosophical ideal, but a practical approach that could be tested and confirmed through experiment. As technology advanced, the principles confirmed by Rowland's experiment found new applications. The understanding that moving charges produce magnetic fields became essential in the development of vacuum tubes, cathode ray tubes, and later, particle accelerators. In all these devices, charged particles move through space rather than through wires, yet they produce and respond to magnetic fields in ways consistent with Rowland's findings. His work thus anticipated technological developments that would emerge decades later. In modern physics, Rowland's contribution is also reflected in how electromagnetic fields are described mathematically. Maxwell's equations treat electric and magnetic fields as interconnected quantities that depend on charge and current. Rowland's experiment gave physical meaning to the current term in these equations by showing that it represents charge motion in the most general sense. This reinforced the idea that mathematical symbols in physical theories correspond to real, measurable phenomena. Rowland's work also connects to later developments in relativistic physics, even though relativity was not yet formulated during his lifetime. The idea that magnetism depends on motion aligns naturally with the relativistic view that electric and magnetic fields transform into one another depending on the observer's state of motion. While Rowland did not interpret his results in these terms, his experiment provided early empirical support for the notion that motion plays a fundamental role in electromagnetic phenomena. The historical significance of Rowland's contribution becomes even clearer when viewed in retrospect. Many scientific advances are incremental, adding small pieces to an existing framework. Rowland's experiment, however, resolved a foundational question and clarified the physical meaning of magnetism itself. It exemplified how a single well-designed experiment can have far-reaching consequences for theory, education, and technology. Rowland's legacy also serves as a reminder of the importance of questioning assumptions. At the time, it was widely accepted that magnetism was inseparable from electric currents in conductors. Rowland challenged this assumption by asking a simple but profound question: what if charge motion alone is sufficient? By designing an experiment to answer this question directly, he demonstrated the power of curiosity guided by careful reasoning. In the broader narrative of scientific progress, Rowland represents the ideal of the experimental physicist who bridges theory and observation. He did not merely accept theoretical predictions, nor did he rely on experimental results without seeking deeper meaning. Instead, he used experiment as a tool to illuminate theory and used theory to guide experimental design. This balanced approach remains a model for scientific inquiry. Today, the principles confirmed by Rowland's experiment are so deeply embedded in physics that they are often taken for granted. Students learn early on that moving charges produce magnetic fields, rarely pausing to consider that this idea once required experimental proof. Rowland's work reminds us that even the most fundamental concepts in science were established through careful observation and experimentation. The enduring impact of Henry Augustus Rowland's contribution lies in its clarity and universality. By demonstrating that magnetism arises from moving electric charge, he helped unify two major branches of physics and provided a foundation for countless future discoveries. His work continues to influence how scientists understand the natural world, how educators teach fundamental concepts, and how engineers design technologies that rely on electromagnetic principles. In the end, Rowland's experiment stands as a testament to the power of precise experimentation in revealing the underlying structure of nature. It shows how a focused investigation into a specific question can lead to insights that reshape an entire field. Through his dedication, insight, and rigor, Henry Augustus Rowland secured a lasting place in the history of physics, and his contribution remains a vital part of our understanding of electromagnetism. The experimental proof that magnetic effects arise from the motion of electric charge represents a crucial turning point in the history of physics. Before such proof was firmly established, magnetism was often treated as a phenomenon closely tied to specific materials, such as iron, or to electric currents flowing through wires. While theoretical ideas suggested a deeper connection between electricity and magnetism, experimental evidence was necessary to confirm that motion itself was the true source of magnetic effects. This proof transformed magnetism from a mysterious property into a predictable and measurable consequence of charge dynamics. Early observations showed that electric currents could influence compass needles, indicating a link between electricity and magnetism. However, an electric current was understood as charge flowing through a conductor, which left open the possibility that the conductor or the structure of the current played a role in creating magnetism. To move beyond this ambiguity, experiments had to demonstrate magnetism produced by charge motion alone, without relying on conventional current-carrying wires. Such experiments required great sensitivity because the magnetic effects produced by small amounts of moving charge are extremely weak. The key idea behind proving magnetic effects from motion was simple in principle, but difficult in practice. If electric charge at rest produces only an electric field, then causing that charge to move should introduce magnetic effects. The challenge lay in creating controlled motion of charge and detecting the resulting magnetic field while ruling out other possible influences. Experimental setups had to be carefully designed to eliminate stray currents, external magnetic fields, and mechanical disturbances that could obscure the true source of the observed effects. One of the most convincing forms of experimental proof involved moving charges mechanically rather than electrically. By placing electric charge on an object and then physically moving that object, scientists could show that magnetism appeared only when the charge was in motion. When the object was stationary, no magnetic effect could be detected. When it moved, even without any current flowing through a wire, a magnetic influence became observable. This direct comparison between rest and motion provided strong evidence that magnetism depends on charge movement. The detection of these magnetic effects required highly sensitive instruments. Magnetic fields produced by moving charges are often extremely small, especially when compared to those produced by permanent magnets or large electric currents. Experimentalists used delicate magnetic needles, coils, or galvanometers capable of detecting minute deflections. The reliability of the results depended on careful calibration and repeated measurements to ensure that the observed effects were real and reproducible. A crucial feature of these experiments was the dependence of the magnetic effect on the direction of motion. When the direction of charge motion was reversed, the direction of the magnetic influence also reversed. This behavior matched theoretical predictions and ruled out alternative explanations. If magnetism were caused by some static property of the charged object, changing the direction of motion would not reverse the magnetic effect. The clear directional relationship between motion and magnetism strengthened the conclusion that motion was the determining factor. Another important aspect of experimental proof was the disappearance of magnetic effects when motion stopped. As soon as the charges ceased moving, the magnetic influence vanished, leaving only the electric field associated with the static charge. This sharp transition between the presence and absence of magnetism provided compelling evidence that magnetism is not an inherent property of charge, but a dynamic effect arising from motion. It demonstrated that magnetism is fundamentally different from static electric effects, even though both originate from the same underlying charge. These experimental results had profound implications for electromagnetic theory. They confirmed that electric current is simply one organized form of moving charge, and that magnetism arises whenever charges move, regardless of how that motion is produced. This understanding unified a wide range of phenomena under a single principle and clarified the physical meaning of magnetic fields. Magnetism was no longer seen as a separate force, but as a natural extension of electric effects in motion. The proof of magnetic effects from motion also influenced how scientists interpreted natural phenomena. It helped explain why moving charged particles in space create magnetic fields around planets, stars, and galaxies. It also provided a foundation for understanding magnetic behavior at the atomic level, where electrons in motion give rise to the magnetic properties of materials. Without experimental confirmation, these explanations would remain speculative. With it, they became firmly grounded in physical law. From a technological perspective, the experimental demonstration of magnetism from moving charge validated the principles behind countless devices. Electric motors, generators, transformers, and communication systems all rely on the interaction between moving charges and magnetic fields. The confidence to design and improve such technologies depends on knowing that these interactions are not coincidental but follow universal and experimentally proven rules. In a broader scientific sense, the experimental proof of magnetic effects from motion illustrates the importance of experiment in validating theory. Mathematical predictions and conceptual models gain their true power only when supported by observation. By demonstrating that moving electric charges produce magnetic fields, experimental physicists provided a solid foundation for electromagnetism as a unified and reliable theory of nature. This proof remains a cornerstone of physics, reminding us that motion is the key that transforms electric charge into magnetism. The role of rotating charged objects in demonstrating magnetic effects is a critical step in understanding how motion of electric charge leads to magnetism. Rotation provides a unique and controlled way to move electric charges without relying on traditional electric currents flowing through wires. By using rotation, scientists were able to separate the idea of charge motion from the conventional concept of current and show that magnetism arises purely because charges are moving, not because they are part of a closed electrical circuit. When a charged object is stationary, the charges on its surface produce only an electric field. This field can attract or repel other charges, but it does not influence magnetic materials or compass needles. However, when the same charged object is set into rotation, every charge on its surface begins to move in a circular path. Even though the object may remain in the same place overall, the individual charges are now in continuous motion. This motion effectively creates a circulating flow of charge, which is equivalent, in physical terms, to an electric current. The importance of rotation lies in its simplicity and clarity. Unlike currents in wires, which involve complex interactions between electrons and the atomic structure of a conductor, rotating charged objects involve direct mechanical motion of charge. This makes it easier to attribute any observed magnetic effect solely to the movement of charge itself. By carefully controlling the speed and direction of rotation, scientists could study how magnetic effects depend on the motion of charges in a precise and predictable way. One of the most significant observations made using rotating charged objects is that the strength of the magnetic effect increases with the speed of rotation. As the object spins faster, the charges move more rapidly, and the resulting magnetic field becomes stronger. This direct relationship between speed and magnetic strength provides strong evidence that magnetism depends on charge motion. If magnetism were an intrinsic property of the charged object, changing the speed of rotation would have no effect on the magnetic field. The observed dependence on speed clearly points to motion as the cause. Direction also plays a crucial role in experiments involving rotating charged objects. When the direction of rotation is reversed, the direction of the magnetic field also reverses. This behavior mirrors what is observed in conventional electric currents, where reversing the direction of current reverses the direction of the magnetic field. The consistency between these two cases reinforces the idea that rotating charges behave like electric currents and produce magnetism in the same fundamental way. Another key aspect of rotating charged objects is the disappearance of magnetic effects when rotation stops. As soon as the object ceases to rotate, the charges return to a stationary state, and the magnetic field vanishes. Only the electric field associated with the static charge remains. This sharp transition highlights the dynamic nature of magnetism and distinguishes it clearly from static electric effects. Magnetism exists only as long as there is motion. Without motion, it cannot be sustained. Experiments with rotating charged objects also helped clarify the relationship between mechanical motion and electromagnetic phenomena. They showed that mechanical energy used to rotate an object can be converted into electromagnetic effects through the motion of charge. This insight deepened understanding of energy transfer and paved the way for later technologies that convert mechanical motion into electrical and magnetic energy, such as generators and motors. At a conceptual level, rotating charged objects provided a bridge between macroscopic and microscopic views of magnetism. On a large scale, a rotating charged disk or sphere demonstrates how collective motion of charge produces a magnetic field. On a microscopic scale, electrons moving in circular paths around atomic nuclei create similar effects. The behavior observed in rotating objects thus mirrors the behavior of charges at the atomic level, helping scientists connect everyday experiments with the fundamental structure of matter. The use of rotating charged objects also addressed skepticism within the scientific community. Some scientists initially questioned whether magnetism could arise without a conventional current. By demonstrating magnetic effects using purely mechanical rotation of charge, these experiments removed doubts and provided clear, direct evidence. They showed that the presence of a conductor or a closed circuit is not essential for magnetism. What matters is the motion of electric charge. From a practical standpoint, understanding the role of rotating charges has influenced many areas of physics and engineering. It contributes to the design of rotating machinery, electromagnetic sensors, and experimental devices used to study charged particles. In advanced research, similar principles are applied in particle accelerators, where charged particles move along curved paths and generate magnetic fields that influence their motion. In a broader scientific context, rotating charged objects helped solidify the unified view of electromagnetism. They provided tangible proof that electricity and magnetism are not separate forces but interconnected aspects of a single phenomenon. By showing that simple rotation of charge can create magnetism, these experiments revealed the elegance and consistency of physical laws. Ultimately, the study of rotating charged objects demonstrated that magnetism is a natural consequence of motion. It emphasized that even without visible currents or wires, moving charges can shape the electromagnetic environment around them. This understanding remains fundamental to modern physics, reinforcing the idea that motion transforms electric charge into a source of magnetic influence and unifying our view of electromagnetic phenomena. The impact of Rowland's experiment on electromagnetic theory was both profound and far-reaching, influencing how scientists understood the fundamental nature of electricity and magnetism. Before this experiment, the connection between electric current and magnetism was known, but the deeper cause of magnetic effects was not fully clear. Rowland's work provided direct experimental evidence that magnetism originates from the motion of electric charge itself. This insight strengthened the conceptual foundation of electromagnetic theory and helped transform it into a unified and coherent framework. One of the most important consequences of Rowland's experiment was the clarification of the meaning of electric current. Previously, current was often thought of mainly in terms of charge flowing through metallic conductors. Rowland's findings showed that current is not limited to wires or specific materials. Any organized motion of electric charge, regardless of the medium or mechanism, can produce magnetic effects. This broader understanding made electromagnetic theory more general and applicable to a wider range of physical situations, including charged particles moving in space. Rowland's experiment also provided strong support for Maxwell's equations, which describe how electric and magnetic fields are generated and interact. While Maxwell's theory predicted that moving charges should produce magnetic fields, experimental confirmation was essential for widespread acceptance. Rowland's work offered clear and direct evidence that aligned with these predictions. As a result, confidence in Maxwell's framework increased, and electromagnetism became firmly established as one of the central pillars of classical physics. The experimental demonstration that magnetism arises from moving charge helped resolve lingering conceptual ambiguities. It became clear that magnetism is not an independent force, but a manifestation of electric phenomena involving motion. This understanding unified electric and magnetic effects under a single theoretical structure, allowing scientists to explain diverse phenomena using the same basic principles. The idea that electric and magnetic fields are two aspects of one electromagnetic field gained strong empirical support from Rowland's results. Rowland's work also influenced how scientists interpreted the sources of magnetic fields in nature. Planetary magnetic fields, solar magnetic activity, and magnetic effects in plasmas could now be understood in terms of moving charges rather than mysterious intrinsic properties. This perspective provided a consistent explanation for magnetic phenomena across vastly different scales, from laboratory experiments to astrophysical processes. Electromagnetic theory thus became a powerful tool for understanding the behavior of the universe. In the realm of material science, the implications were equally significant. The magnetic properties of materials could be traced back to the motion of electrons within atoms. Rowland's experiment reinforced the idea that microscopic charge motion is responsible for macroscopic magnetism. This insight later became central to the development of atomic and quantum theories of magnetism, linking classical electromagnetism with emerging ideas about the structure of matter. Another important impact of Rowland's work was methodological. It demonstrated the value of carefully designed experiments in testing and refining theoretical ideas. By isolating charge motion from conventional currents, Rowland showed how subtle experimental approaches could address deep conceptual questions. This approach influenced later experimental research in electromagnetism and encouraged physicists to seek more direct and precise tests of theoretical predictions. The influence of Rowland's experiment extended into technological development. A clear understanding of how moving charges produce magnetic fields is essential for designing electrical machines, communication systems, and scientific instruments. By confirming the fundamental principles underlying these technologies, Rowland's work provided a reliable theoretical basis for innovation. Engineers could design devices with greater confidence, knowing that electromagnetic behavior followed well-tested laws. Rowland's findings also prepared the ground for later advances in physics, particularly in relativity. The idea that magnetic effects depend on motion aligns naturally with the relativistic view that electric and magnetic fields are interconnected and observer-dependent. Although relativity had not yet been formulated, Rowland's experiment supplied empirical evidence that motion plays a central role in electromagnetic phenomena. This made the later unification of electricity, magnetism, and relativity more intuitive and compelling. In educational terms, the impact of Rowland's experiment was substantial. It provided a clear and concrete example of how abstract electromagnetic concepts correspond to real physical effects. Students and researchers alike could point to experimental proof that moving charges create magnetic fields, reinforcing the unity of theory and observation. This helped shape how electromagnetism was taught and understood in academic settings. Overall, the impact of Rowland's experiment on electromagnetic theory lies in its ability to clarify, unify, and strengthen the understanding of electric and magnetic phenomena. By demonstrating that magnetism arises from the motion of electric charge, it removed ambiguity, supported theoretical predictions, and expanded the scope of electromagnetic theory. Its influence continues to be felt in physics, engineering, and education, making it a cornerstone in the development of modern science. The relevance of the principle demonstrated by Rowland's experiment to modern physics and technology is both deep and widespread. The idea that moving electric charges create magnetic fields is no longer just a laboratory curiosity. It is a foundational concept that underpins many of the scientific theories and technological systems that define contemporary life. From fundamental research to everyday devices, this principle continues to guide understanding and innovation. In modern physics, the motion of electric charge is central to the study of particles and fields. Charged particles such as electrons, protons, and ions are constantly in motion in natural and artificial environments. Their behavior is governed by electromagnetic forces, which are described using the same principles confirmed by Rowland's experiment. In particle accelerators, for example, electric fields are used to accelerate charged particles to extremely high speeds, while magnetic fields are used to bend and focus their paths. The predictable relationship between charge motion and magnetism allows scientists to precisely control particle trajectories and study the fundamental structure of matter. Astrophysics and space science also rely heavily on this principle. Magnetic fields observed around planets, stars, and galaxies are now understood as the result of large-scale motion of charged particles. The Earth's magnetic field, which protects the planet from harmful solar radiation and enables navigation, is generated by the movement of electrically charged material in its molten core. Similarly, the sun's magnetic activity, responsible for phenomena such as sunspots and solar flares, arises from complex motion of charged plasma. Without the understanding that moving charges generate magnetic fields, these cosmic phenomena would remain unexplained. In the realm of quantum physics, the motion and intrinsic properties of charged particles play a key role in magnetic behavior. Electrons possess both electric charge and intrinsic angular momentum, known as spin, which contributes to magnetic effects at the atomic level. Modern theories explain magnetism in materials by examining how electrons move and interact within atoms and solids. Technologies based on these principles, such as spintronics and magnetic storage devices, depend on precise control of electron motion and magnetic interactions. The technological impact of charge motion and magnetism is especially visible in electrical engineering. Electric motors, which convert electrical energy into mechanical motion, operate by exploiting magnetic fields produced by moving charges in coils. Generators work on the reverse principle, using mechanical motion to move charges and produce electric currents. These devices are fundamental to power generation and distribution systems worldwide. The reliability of modern electrical infrastructure depends on the predictable relationship between moving charges and magnetic fields. Communication technologies also rely directly on this principle. Wireless communication involves accelerating charges in antennas, which generates electromagnetic waves that travel through space. Radio, television, mobile phones, and satellite communication all depend on the interaction of electric and magnetic fields produced by moving charges. The clarity and speed of modern communication systems are possible only because these electromagnetic processes are well understood and precisely controlled. Medical technology provides another important example of relevance. Magnetic resonance imaging, or MRI, uses strong magnetic fields and radio frequency electromagnetic waves to produce detailed images of the human body. The operation of MRI machines relies on the behavior of charged particles and their magnetic interactions at the atomic level. Advances in such medical technologies continue to depend on deeper understanding of electromagnetism and charge motion. In computing and data storage, the principle demonstrated by Rowland'S experiment remains essential. Information in many storage devices is encoded using magnetic states, which are manipulated through electric currents and charge motion. Even in modern semiconductor technology, where electric effects dominate, magnetic interactions are increasingly important for improving performance and efficiency. Emerging technologies seek to integrate electric and magnetic control at the nanoscale, reflecting the continued relevance of electromagnetic principles. The principle also plays a crucial role in renewable energy technologies. Wind turbines and hydroelectric generators rely on electromagnetic induction, where mechanical motion causes charges to move and generate electric power. Solar energy systems, while based primarily on electric effects, also involve charge motion and electromagnetic interactions in their operation and control systems. Understanding how moving charges interact with magnetic fields helps improve the efficiency and reliability of these technologies. In scientific research, the legacy of Rowland'S experiment continues to inspire new investigations. Advanced experiments explore electromagnetic behavior under extreme conditions, such as very high energies, strong fields, or low temperatures. These studies often test the limits of existing theories and seek deeper unification with other fundamental forces. Yet even at these frontiers, the basic idea that moving charges create magnetic fields remains valid and essential. On a broader level, the relevance of this principle extends to education and scientific thinking. It provides a clear example of how experimental evidence can reveal deep connections in nature. By showing that a simple concept, charge in motion, leads to a wide range of phenomena, it encourages a unified and systematic approach to understanding the physical world. This perspective helps students and researchers alike appreciate the coherence and elegance of physical laws. In everyday life, People may not be aware of the principle demonstrated by Rowland's experiment, but they experience its effects constantly. From using electronic devices and transportation systems to accessing medical care and communication networks, modern society depends on technologies rooted in electromagnetic principles. The reliability and sophistication of these technologies are a testament to the enduring relevance of the idea that moving electric charges produce magnetic fields. Ultimately, the relevance of Rowland's experiment to modern physics and technology lies in its foundational nature. It confirmed a principle that connects theory with experiment, microscopic behavior with macroscopic phenomena, and scientific understanding with practical application. This principle continues to shape the way scientists explore the universe and the way engineers design the systems that support modern life.